An exponential function is a function in which the variable is an exponent. What would that look like? When we say something is a function, we begin with functional notation. F of x equals something. Now, since the variable must be an exponent, we need a constant or a number to the power of x. So, f of x equals 7 to the x, f of x equals 1/2 to the x, and f of x equals 0.4 to the x are all examples of exponential functions. Is f of x equals x squared an exponential function? No, the variable has to be the exponent. So exponential functions are defined where a, or the constant, is greater than 0 and x is any number. So looking at this function, f of x equals a to the x, what is its domain? X can go from negative infinity to infinity. What is the range? Well, y approaches 0 but never quite touches it. So open bracket, 0 to a positive infinity. Where is it increasing? From negative infinity to positive infinity. Where is it decreasing? It's not. And what is the y-intercept? The 0.01. Looking at the graph of f of x equals a to the negative x, what is its domain? Again, negative infinity to infinity. How about its range? Once again, we have the values of negative infinity to 0, but not including 0, so open parentheses. Where is it increasing? It's not. Where is it decreasing? From negative infinity to infinity. And what's the y-intercept? Once again, we see 0, 1. Sensing a pattern there. Okay, so let's substitute an actual number in for a. In this example, we'll look at f of x equals 2 to the x. So let's do the easy one first. Let's start out with x equals 0. When we take 2 and raise it to the 0 power, anything to the 0 power is what? Anything to the 0 power is 1. Then let's work with the positive numbers. When f of x is 2 to the x and we substitute 1 in for x, we get 2. And if we substitute 2 in for x, 2 squared is 4. Looks like I need to zoom out a little bit here. Now let's try the negative values. 2 to the negative 1 power means drop it to the denominator and it becomes 1/2, otherwise known as 5/10. And then 2 to the negative 2 means take it to the denominator and we'll have 1 over 2 squared, or 1/4, otherwise known as 25/100. Let's see what it looks like when we connect the dots. So let's talk about what we've learned about families of graphs. Here's our basic parabola, f of x equals x squared. What will happen if I subtract 4 from the value of x before I square it? It's going to shift, right? Which way? It shifts to the right 4 steps. What happens if I add 5 to the value of x squared? Again, it shifts which way? it will shift vertically 5 steps. And what happens if I take 2 times x squared? It stretches it. Does it become narrower or wider? It becomes narrower. Recall that when working with families of graphs, and you take a function and compare it to its parent, if f of x equals a times the quantity x minus h plus k, a stands for the stretch, how much it's going to expand or contract it. So if a is a value that is greater than 1, it will actually shrink it. And if it is a value that is a fraction, it will stretch it, make it wider. As far as h goes, the horizontal movement, that comes into play to shift it to the left or to the right. So the way I remember it is if I have a positive value here with x, we want to get the solve for the x, so we bring it to the other side and it will shift it to the left that number of steps. If it was negative here with x and we take it to the other side, it will become a positive value, so it will shift it to the right that number. Likewise, k stands for your vertical movement, and since the y value, which corresponds to the vertical movement, is on the opposite side of the equation from k, when you have a positive value for k, it will move it vertically, that number, to upward that number, and if it is a negative value for k, it will drop it down that number. So if f of x is equal to 2 to the x, what will happen with g of x when it is 2 to the x plus 3? Well, since the 3 is with the x, it's going to be shifting it horizontally. Now, does it move it 3 steps to the left or 3 steps to the right? To the left. What about the transformation when h of x is equal to 2 to the negative x minus 4? Well, that negative x is going to reflect it across the y-axis. And the negative 4 is the vertical movement, so it will shift it down 4. Okay, we have another exponential function to talk about, but before we can do that, I need to introduce a number for you called e. E is an important number in calculus limits, in continuously compounded interest, and also in exponential decay. It is an irrational number. We approximate it to 2.718281, and it is the base in the natural log. The natural log is notated as ln. So the natural log is the same thing as the log base e, which is approximately equal to log base 2.718. So now that you know a little bit about e, let's talk about two formulas for compounding interest. So the first formula is a equals p times the quantity 1 plus r over n, all to the nt power. This is a formula for compounding n times per year. So a stands for the amount of money earned or owed. P stands for the principal, the initial amount loaned or invested. N is the number of times that you are compounding that interest per year. R is the rate at which you are earning or loaning that money. It's as a decimal. and then T is the number of years that the note or the investment is for. The second compound interest formula is one for continuously compounding interest. And again, A stands for the amount, P stands for the principal, E is our number we just introduced a moment ago, R is the rate once again, and T is the amount of time. Okay, so let's look at those two formulas in action. If you loaned a bank $10,000 at a 5% interest rate for 10 years, find out the amount that you would have in the bank if it's compounded, first of all, monthly, and second of all, continuously. So let's write the formulas down. Compounding monthly, we would use the formula A equals P times 1 plus R over N to the NT power. So our amount is going to be equal to the principal, which is $10,000, times 1 plus our rate of 5%. 5% as a decimal is 5/100ths. And it is being compounded monthly, so the number of times per year is 12. And then again, we'll use the 12 for our N, and we're looking at this in 10 years. So T is 10. So working that out, we have 10,000 times 1 plus, can't do this in my head, so I'll take 5/100ths divided by 12, and rather than clear the calculator, I'll add 1 to that. Now that's the value in the parentheses. So we're going to take that and raise it to the 120th power. And we will get our value that we're taking times 10,000. So after the 10 years, we will have an amount of $16,470.09. Let's go back and check our work really quickly. 5/100ths divided by 12. 0.0416 repeating. That was being taken times to the 120th power. Now let's talk about the continuously compounded interest. The formula for that was A equals P times E to the RT. So again, our principal was 10,000. E is that number, 2.71 approximately, and R is 0.05. T is 10 years. So we'll pull up our handy calculator once again. 0.05 times 10, it's an easy number, 5/100ths, 5/10ths, and we will take e to that power, so we need the inverse here of the natural log. We need e to the 5/10ths, and we're going to take that value times 10,000. $16,487 and 21 cents. Once again, I got a little ahead of myself here, so let's write this in. 10,000 times e to the 5/10, and then it's calculator work from there.